Hello, my name is Dr. Evan James Gowan, but you can call me Evan. I'm a paleoclimate scientist who studies such topics as sea level, ice sheets, and climate change. In this video, I will present the Global Archive of Paleo Sea Level Indicators and Proxies, or GAPSLIP, and its application to assessing past ice sheets. I gave this presentation at last month's Japan Geoscience Union conference, which was held in Chiba. Before I start, I wanted to announce that I will soon launch a new podcast called the Raised Beaches Podcast. In this podcast, I will discuss topics including paleoclimate, earth science, and global change. You can follow me on Mastodon and on Blue Sky for updates on this. The links are in the description below. And now on to the presentation. The world is currently experiencing an ice age. Antarctica and Greenland are currently covered in vast sheets of ice that contain a lot of water volume. Ice caps and glaciers cover mountain ranges all over the world. However, during the past 3 million years or so, in a period known as the Quaternary, ice sheets also covered northern Europe and northern North America. These ice sheets grew and retreated as a result of changes to the Earth's orbital configuration. Over time, the Earth's axis of rotation slowly changes. This is a result of the influence of the gravitational attraction of the planets and the Sun. When the Earth's axis of rotation is pointed away from the Sun during the Northern Hemisphere summer, it becomes difficult for the snow that accumulates in the wintertime in northern North America and Europe to melt away. Over time, this snow accumulates and it forms an ice sheet. In addition, the Earth's carbon dioxide concentrations also change through time. This influences the size of the ice sheets, but it's more of an amplifying factor to these orbital changes. The goal of my research is to deduce the size of these ice sheets and their history through time. One way to deduce the history and size of past ice sheets is to investigate a process known as glacial isostatic adjustment, or GIA. There are three main components of GIA. The first is that as the ice sheet builds up, it takes water out of the ocean. This causes global average sea level to fall. The second aspect is that as the ice piles up on the land, it puts a lot of pressure on the surface of the Earth. This causes the Earth's surface to deform. The uppermost part of the Earth is a layer known as the lithosphere. The rocks in the lithosphere are relatively cool, and they will deform instantly as you apply the load of the ice. Deeper below the lithosphere is the mantle. The mantle rocks are much hotter, and over time they tend to flow away from the center of the ice load. This is known as viscous deformation. The third aspect of GIA is that loading the ice on the surface will change the Earth's gravitational field. Because you put the mass of ice in the northern hemisphere, this causes the ocean water to gravitationally attract towards the northern hemisphere. The sum of the deformation and the gravitational attraction changes means that sea level around the world will rarely match the global average sea level. When the ice sheets start to melt or retreat, these GIA processes will reverse. The melting water will go back into the ocean, and this causes global average sea level to rise. With the ice melting away, this reduces the pressure on the Earth's surface. This causes the Earth to rebound. Because the mantle rocks are acting in a viscous way, it takes time for those rocks to flow back to where they originally were. The gravitational field will also go back to normal. This causes the water to preferentially go back into the southern hemisphere. If you measure past sea level changes in a bunch of different areas, using this knowledge, you can deduce the size and history of the ice sheets. So now that we know that the GIA processes will cause sea level to vary through space and time around the world, how do we measure past sea level? Well, we have to go around the world and find geological proxies of past sea level position. As an example, a beach ridge is a landform that will be created a few meters above sea level due to the action of storm waves. If you find a fossil beach ridge, what you do is you measure the elevation of that beach ridge, preferably with a highly accurate technique like differential GPS, and compare it to the elevation of a present-day beach ridge relative to current sea level. Using this analog, you can deduce what the past sea level position was relative to present. You also need to find the age of the beach ridge. For beach ridges that have formed within the past 30,000 years or so, you can use radiocarbon dating of shells. For older beach ridges, you need to use other techniques, such as uranium-thorium dating. By going around the world and measuring geological proxies, you can start to deduce the pattern of GIA. Over the past 2 centuries, scientists from around the world have been gathering geological proxies of sea level change. However, this has often been done in a very ad hoc way. As a result, in 2008, PaleoMIST formed. PaleoMIST is a global community of sea level researchers. They seek to standardize the reporting of sea level information. From this, there have been 2 major archival projects. The first is HALSEA. HALSEA focuses on the Holocene, which is the past 12,000 years. They have gathered sea level proxy information from various regions around the world. The second is the World Atlas of Last Interglacial Shorelines, or WALLACE. They've been collecting information on sea level during past warm periods, especially the last interglacial, which happened about 12,000 years ago. As someone who models past ice sheets and sea level, I'm very thankful for these initiatives to compile paleo sea level data. However, these databases are often not in a format that makes it easy to compare the modeled sea level to the data. In addition, sometimes these datasets need updated. For instance, if a new radiocarbon calibration curve is published. As a result, I've created the Global Archive of Paleo Sea Level Indicators and Proxies, or GAPSLIP. This database is available freely on GitHub. Next, I will go through what is inside GAPSLIP. GAPSLIP contains the data in its original format, as well as in a format that I created myself. There are a series of scripts that will go through this data and separate it into separate, smaller regions. It will also apply a reservoir age to any marine-based radiocarbon date. There's a script that will calibrate all of the radiocarbon dates using Oxcal. All of this is in the GitHub repository, so you don't have to do this yourself. Next, there's a folder called LaTeX. This contains the scripts that will plot the model data comparisons, as well as gathering all of the plots together into a fully cited report. GAPSLIP also contains a number of proxy-based sea level records that are generated from marine isotope records. The sea level data model comparison in GAPSLIP is easy. All the user needs to do is to calculate the sea level at the location of all the data points in the database. There's a script using generic mapping tools that will create the plots. This includes a plot of a small map showing the location of all the data. It also shows the calculated sea level and data together on the same plot. It also gives a score. This score is the sum in meters of the discrepancy between the calculated sea level and the data. Like golf, a lower score is better. The kinds of data that you'll see on these plots includes index points, terrestrial limiting data, and marine limiting data. The index points define sea level within a certain range. This includes data like the beach ridges that I mentioned before. The second is terrestrial limiting points. This means that sea level must be below the elevation of the sample. This includes archaeological sites. The third are marine limiting points. In this case, sea level should be above the elevation of these samples. This can include marine clay. The latest release of GAPSLIP, version 2.1, came out in December 2023. However, I've been actively adding new data since then. Currently, there's over 14,800 data points from over 1,700 different studies. The data coverage includes most of the northern Atlantic regions of North America and Europe, Greenland, Australia, Southeastern Asia, and Antarctica. Most of these data come from Halsey and Halsey compatible data sets. I've also included data from the periods known as marine isotope stages 3 and 4, which covers 27,000 years ago to 70,000 years ago. Next, I will demonstrate the utility of GAPSLIP by showing a data model comparison of the Greenland Ice Sheet. Since there was no previously published database of Greenland sea level data, I did this myself. The details of the Greenland sea level data in GAPSLIP are published in the 2023 issue of the GEUS Bulletin. The modeled sea level that I'm about to show comes from a global ice sheet reconstruction called PaleoMIST. PaleoMIST is a preliminary reconstruction of the ice sheet history over the past 80,000 years, using a very coarse time step of 2,500 years. This means that it's not really appropriate to use this to model the fine details of sea level changes using GIA methods. That is not to say I did not use some sea level information to guide this model. I used sea level information from the center of the North American and Eurasian ice sheets to ensure that the volume of the ice sheets was relatively appropriate. However, smaller ice sheets like Greenland were not evaluated against the data. As a result, it's unknown if PaleoMIST is appropriate in those regions. Because the 2,500-year time step in PaleoMIST is so coarse, I've interpolated it to 500-year time steps to make a more fair assessment of the calculated sea level versus the data. Here are some of the details of the ice sheet reconstruction of Greenland in PaleoMIST. The maximum extent of the Greenland ice sheet was maintained until about 15,000 years ago. This maximum extent comes from a previous publication by Funder et al. 2011. From 15,000 years ago to 7,500 years ago, the margin is set to retreat to its present-day configuration. At 5,000 years ago, the ice is set to be retreated compared to the present-day configuration in western Greenland. This is consistent with some of the observations we have. In order to assess the volume that was added to the Greenland ice sheet during the glacial period, we use a unit called sea level equivalent ice volume. This is the volume of ice divided by the present-day ocean area. This is a unit of convenience that helps visualize how much sea level would rise if that ice melted. As we can see, at the glacial maximum, the amount of extra ice in the Greenland ice sheet in the PaleoMIST reconstruction is about 3.5 meters. The sea level equivalent of 3.5 meters in PaleoMIST happens to be intermediate of some other Greenland ice sheet reconstructions that have been published. It is more than the value that is reported in ICE 5G and ICE 6G by Peltier et al. It is comparable to the value used in the Australian National University ice sheet reconstruction. It is also less than what is reported by the Simpson and Lecavier et al. Models. The maximum extent of the Greenland ice sheet in PaleoMIST was based on a study by Funder et al. They hypothesized that the maximum extent of the Greenland ice sheet, the last glaciation, did not reach the continental shelf edge. However, recently collected data, which was summarized in a paper by Leger et al., suggests that the ice margin could have reached the continental shelf edge. As a result, the GIA signal from PaleoMIST will probably be underestimated. There are a total of 1,019 data points for Greenland in the GAPSLIP database. This was a very fruitful exercise to compile these data, as I got to learn about the long history of investigations in Greenland. As you can see, the distribution of data is not equal around Greenland. Places such as southeastern Greenland don't have a lot of data. This is due to the inaccessibility of Greenland. In these places, it's hard to get there because there's sea ice and icebergs, which make going there by boat difficult. Also, there are no towns, so you can't simply just fly there. There are sea level data in Greenland covering the past 12,000 years. The general characteristic of sea level change in Greenland is that there's an initial high stand and then a gradual reduction in sea level to present-day values. This is caused by the relaxation of the mantle back to where it originally was before the ice loaded on top. The calculated sea level in PaleoMIST is unable to reach those high stand values. This points towards the idea that the ice margin reached the continental shelf edge, as suggested by Leger et al. However, it's important to remember that the calculated sea level is not only dependent on the ice load history, it also depends on your assumptions on the Earth's structure. Greenland was affected by the Iceland hotspot, which is currently under Iceland and is producing all the magnificent volcanic eruptions that have been going on the past couple of years. The passage of the Iceland hotspot under Greenland caused the lithosphere to thin. In PaleoMIST, I assumed a lithosphere thickness of 120 kilometers. This is appropriate for North America, but in places that were affected by the Iceland hotspot, this is probably too thick. I did an experiment where I reduced the thickness of the lithosphere to 60 kilometers. And as you can see, in some areas, this did improve the fit of the calculated sea level to the data. It didn't work everywhere. In the south, it didn't work at all. This is one of the complications when dealing with ice sheet reconstructions. I also tried an experiment where I increased the thickness of the ice sheet without changing the margin location. This was done by changing a parameter in the program that I used to calculate the ice sheet reconstruction. Most of this ice is piled up all over the ice sheet and not focused in any one location. As you can see by this result, it had less of an effect than changing the lithosphere thickness. This again points to the idea that the margin history needs to be revised in a future version of PaleoMIST. To wrap things up, I hope that GAPSLIP will prove to be a useful data set for GIA modelers. The next version of GAPSLIP will have over 15,000 data points. If you want more information on GAPSLIP, please read my recently published paper in the GEUS Bulletin, which is available from the link in the description. Thank you so much.